Hi guys, in this video we're going to go ahead and go through section 1.7 on periodic trends. So you did an activity in class where you looked at some of those. I want to have you guys go ahead and go through your notes and some of those things that go along with what we did in the activity in class. I'll go through quickly, and then there's some additional things that you need to know that go along with those trends. So here we go. All right, let's go ahead and start with atomic radius. So when we talk about, we are going to talk about atomic radius and also ionic radius. So when we're dealing with atomic radius, we're talking about basically the size of the atom, how big it is, and ionic radius, how big that particular atom is when it becomes an ion, whether it becomes positive or negative. So before we get into the ionic radius, let's go ahead and talk about the atomic radius. So you guys need to know some trends about that. You looked at some diagrams in class and saw that as you go across a row, atomic radius decreases. So it's important for you, yes, to know the trend, but really important for you guys to understand why that happens. And it has to do with the nuclear charge. So for example, let's take a look at just row 2 on the periodic table. So in row 2, we go from lithium all the way to neon, and lithium has 3 protons in the nucleus, and it has 2 energy levels with electrons. Okay, this is lithium. Every element in row 2 has 2 energy levels. So as we go across, you're not changing how many energy levels you have, you're only changing how many protons are in the nucleus. As you get to neon, neon has 10 protons and still 2 energy levels. Those aren't great circles, but what happens is, because the nucleus of neon is much stronger than the nucleus of lithium, those electrons, those energy levels get pulled in closer because the nucleus is stronger. And because the nucleus is stronger, it's going to pull those energy levels in closer, and so the atoms are going to get smaller as you go across. Okay, as you go down a group, you're going to have an increase in size. Specifically just because you're dealing with more energy levels. If you're in energy level 1, there's 1 energy level, or row 1, you have 1 energy level. Row 2 has 2 energy levels. Row 3 has 3 energy levels, and so on. And so the more energy levels you have, that is obviously going to increase in size. Even though there's more protons down here, just the fact that there are more electrons, they're going to take up more space. So they're going to be larger in size. So you need to know the trends. You need to be able to answer why those trends exist. Okay, so let's talk about ions. When we have atoms, neutral atoms, they don't have a charge, and then some atoms gain electrons, some atoms lose electrons. So let's talk about when electrons are gained first of all. So those are going to be our nonmetals. When you have a nonmetal that gains electrons, so let's talk about oxygen. Oxygen has 8 protons and 8 electrons, okay? Now, just to kind of understand what's going on here, in the first energy level, even though they're not all circular, we talked about that with electron configuration, 2 electrons in that energy level, and then in the second one, there's 2 in the S, and then there's 4 in the P, but total that's 6 electrons. 1, 2, 3, 4, 5, 6. Okay. Now, if oxygen is going to gain electrons, it's going to gain electrons in order to fill its outer shell, right? So if its electron configuration is 1s2, 2s2, 2p4, oxygen wants to gain 2 electrons. So when it gains 2 electrons, it fills up that last p orbital, and you end up with 8 electrons instead of 6. Now, electrons are all negatively charged, and so when you take more electrons and you put them in the same amount of space, there's going to be more electron repulsion, because since they have the same charges, they're going to repel each other. So these electrons are going to be repelling these electrons, and then they're going to push farther away. And so when you talk about why the atomic radius increases when electrons are gained, it's not just simply because there are more electrons, it's because those electrons repel each other. So that's the key word. It's electron-electron repulsion. And then the opposite is true. When you lose electrons, by the way, those are our metals, right? So let's talk about lithium again, just because that doesn't have a lot of electrons to work with. Lithium has 3 protons and 2 electrons in the 1s and 1 electron in the 2s. So when lithium becomes an ion, this last electron is lost. And so that energy level is empty, and you only have the 2 electrons that are in the first energy level. So if you have less electrons, then you're going to have less electron repulsion, and then that atomic size is going to decrease. Okay, let's go ahead and talk about this term isoelectronic. Isoelectronic ions are ions that have the same number of electrons. So what we want to do is we want to look at these, and let's talk first of all about how many protons they have. So oxygen is atomic number 8. It has 8 protons. Fluorine has 9 protons. Neon has 10. Sodium has 11. I'm just going by atomic number. Magnesium has 12 protons. If I go through and talk about their neutral atoms, so oxygen, if it was neutral, would have 8 protons and 8 electrons. But since it has a charge of -2, it means it has 10 electrons. Fluorine, again, a neutral fluorine atom would have 9 electrons, but it's negatively charged, so it has 9. I'm sorry, it would normally have 9 electrons, but it has 1 more, so it has 10 electrons. Neon has no charge, so it has 10 electrons. Sodium has a +1 charge, so that means it's lost an electron, so it has 10 electrons. Magnesium has lost 2 electrons. It also has 10 electrons. So these are all isoelectronic because they have the same number of electrons. And what you need to basically be able to identify from this is if you have a list of isoelectronic ions, you need to figure out which ones are going to be bigger and which ones are going to be smaller in size. So the one that has, it goes back to our atomic radius trend, and that the atom with the stronger nucleus, so magnesium having 12 protons versus oxygen having 8 protons, the one with the stronger nucleus is going to be smaller. So magnesium is going to be the smallest ion out of all of those. Oxygen with the weakest nucleus is going to be the largest. All right, let's go ahead and talk about ionization energy. So first definition for ionization energy. Remember we talked about in class the other day that ionization energy is the amount of energy it takes to remove an electron from an atom. And so some atoms really like their electrons and they hold on to them very strongly. Other elements get rid of their electrons very easily. So our nonmetals generally have high ionization energy values because they like their electrons, they don't get rid of them, they actually get extra electrons. Metals generally have very low ionization energy values. Because they get rid of their electrons very easily. Okay, so first ionization energy is specifically the amount of energy required to get rid of the very first electron. And as you go across, ionization energy increases because we have our nonmetals over here. Also, it's related to atomic radius, right? As we go across, we know that these are going to be smaller atoms over here. And if they're smaller atoms, that means the electron is closer to the nucleus, and so it's harder to remove. When you're answering questions about periodic trends, you can't just say it increases as you go across. You have to say, as you go across the row of the periodic table, the electrons are closer to the nucleus, and that makes it more difficult to remove. Same thing when we're talking about going down a group. Okay? The atoms down at the bottom of the periodic table are larger in size, which means the electrons are farther from the nucleus, so they have lower ionization energy values, meaning it's easier to remove those electrons. Okay, there are some exceptions to this trend of increasing as it goes across and decreasing as it goes down. So those exceptions are at 2 spots in the periodic table. We have beryllium to boron, and then nitrogen to oxygen. So in order to understand this a little bit, we need to talk about their electron configurations. So let's talk about beryllium and boron. When we write out the electron configuration for beryllium, we have 1s2, 2s2. It only has 4 electrons. When we write our electron configuration for boron, we have 1s2, 2s2, and then 2p1. It has this extra 2p electron. So normally the trend is that ionization energy increases as you go across, but instead, as you go from beryllium to boron, you're going to have a decrease in ionization energy. And the reason why is because something that they call electron shielding. So in beryllium, we have our nucleus, and then we have 2 energy levels with electrons. In boron, we have our nucleus, and then we have 3 energy levels with that valence electron out there in that third area, that 2p energy level. Now, because this one is farther away from the nucleus and, well, it's in an extra level, it's also shielded. So these 2 energy levels shield this electron from the pull of the nucleus. And so this is much easier to remove than an electron from this energy level in beryllium because of that electron shielding. Now for nitrogen and oxygen, let's again look at electron configurations, and even more so, not just electron configurations, but orbital diagrams. So for nitrogen, I'm going to have 1s2, 2s2, and then 2p3. For oxygen, I'm going to have 1s2, 2s2, 2p4. So if you notice, the difference between these is oxygen has 1 extra electron, and because of that 1 extra electron right here, you have electrons that double up in one orbital. Now, even though they have opposite spins and they're okay to be in the same orbital, they still repel each other. So because they're in the same orbital, you have electron repulsion between those 2. And so this electron is much easier to remove because the other electron is already trying to push it out. So electron repulsion is the reason why as you go from nitrogen to oxygen, you have a decrease again in ionization energy. Those are the 2 exceptions to the rule. It also happens not just for beryllium and boron and nitrogen and oxygen, but everything below those 2. So beryllium and boron, you also have below beryllium, you have magnesium and then aluminum. So the same exceptions occur there, and for the same reasons. Same with nitrogen to oxygen and all of the elements below those. So phosphorus to sulfur. You'll be asked to explain all of those exceptions to the ionization energy rule. Okay, so I want you guys to take a look at this. So this example right here, I'm going to have you answer these in the questions. Which has the highest ionization energy, first ionization energy? And which one has the lowest second ionization energy? So First ionization energy is how much energy is required to remove the first electron. The second ionization energy is how much energy is needed to remove the second electron once one electron is already gone. So think about that. A, B, and C are your choices here, and I'll have you guys go ahead and answer that in the questions. All right, let's go back here. Let's take a look at these ionization energies. So these are really common questions to be given a data table like this, where you have first, second, third, fourth, and fifth ionization energies, which is how much energy it takes to remove the first, the second, the third, the fourth, and then the fifth electron. So as you start to look at these numbers, okay, joules, kilojoules are just a unit of energy. It takes 801 kilojoules of energy to remove the first electron from this element. We don't know what this element is yet. We're going to figure that out, possibly. Oh, maybe not quite. So I go 801, then it takes 2,430 to get rid of a second electron, and then 3,660 to get rid of a third electron. Now, the fourth electron jumps all the way up to 25,000 kilojoules of energy. So when you get a chart like this, what you want to look for is you want to look for that big jump in ionization energy. That's going to be really a very important thing for you to notice, because what that tells you is when you're switching from one energy level to another. So in this particular atom, if I have my proton here, I have 3 electrons out here, and then once all 3 of those are gone, that fourth electron has to come from an energy level that's closer to the nucleus, which is much harder to do, requires so much more energy. That's why you have such a big number right here. So what that tells you, where that big jump is that there are 3 valence electrons. And that's important, because that also tells us that this particular atom is going to have a charge of +3, because when it loses those 3 electrons, now my overall charge of that ion has a charge of +3. Okay, so based on the information in the table below, how many valence electrons? We answered that question. There are 3. What is the charge? If it's going to lose electrons, so it's going to have a charge of +3. Now it says, what is the formula of the compound when the element X combines with oxygen? So element X, by the way, X is not an actual element, we just don't know what it is, has a charge of +3. Oxygen has a charge of 2-. So then we just have to write our formula, X2O3. So anytime you're given a chart of ionization energy numbers, that's what you want to look for, is that big jump, so you can figure out how many valence electrons and what the charge is going to be. All right, we're going to go ahead and talk about electron affinity. Electron affinity is kind of a weird idea. It goes along with ionization energy a little bit, because it has to do with atoms gaining and losing electrons. So when we talked about ionization energy, that was how much energy it takes to remove an electron. Electron affinity is how much energy it takes, or how much energy is either gained or released to gain an electron. So if I start with a neutral atom and it gains an electron and it becomes negatively charged, there's a certain amount of energy that's released. That amount of energy that's released in that process is called the electron affinity. So basically what you have to know about electron affinity is that when we have negative electron affinity numbers, it means that energy is being released when electrons are gained. That's when we're going to be dealing with nonmetals. Okay, anytime energy is released, that means that it's a favorable process, and so it'll happen kind of spontaneously on its own. So negative electron affinities are our nonmetals that always want to become anions and gain those electrons and become negatively charged. Positive electron affinities is when energy has to be absorbed. Those are going to be atoms that don't want to gain electrons. Those are going to be our metals, because metals want to lose electrons. So if metals gain electrons, it's going to require an input of a lot of energy, so they're going to have positive electron affinity values. Basically, what you want to know is the farther you go across the periodic table, the more they want to gain electrons. Over on the right side, these guys gain electrons. Over on the left side, they lose electrons. Those are positive electron affinity values, negative electron affinity values. All right, last thing we're going to talk about in this section is electronegativity. And that's basically how much an atom wants to attract an electron. So again, nonmetals, all of these are all going to have high electronegativity values. And generally, all these metals over here have low electronegativity values. Again, we know that metals want to lose electrons, not gain electrons, so they have low electronegativity values. Nonmetals want to gain electrons, so they have high electronegativity values. So it goes on a scale of 0 to 4, 4 being the most electronegative. So fluorine is our element on the periodic table with the highest electronegativity. That's really important to remember because everything else is kind of compared to fluorine. Fluorine wants to gain electrons more than any other element on the periodic table. Cesium doesn't care about its electrons at all, has the lowest electronegativity value. So you can see as you go from bottom left to top right, you have electronegativity increasing as you go from bottom left to top right. Noble gases, it's important for you guys to know, noble gases do not have electronegativity values. So if we talk about a noble gas like neon, neon has an electron configuration of 1s2, 2s2, 2p6. All of its energy levels are completely full. And because all the energy levels are completely full, there's nowhere to put extra electrons. So noble gases don't want to gain extra electrons, so they're just not even assigned electronegativity values at all. All right, you guys, that's it for the periodic trends for ionization energy, atomic size, electronegativity. You guys have a worksheet 1C to work through in discussing all of these different trends that I went over in the notes. So I will see you guys in class.